Hi students, today we are going to see a new topic, okay, that is the application of Gauss's theorem. In the previous video I told you that after I explain what is Gauss's theorem and what is the proof of Gauss's theorem, I explained that there are three more topics coming. Please wait for. This is the first topic, electric field intensity due to a thin infinite plane sheet of charge. Okay. Many times asked in the board paper. If you look into any previous year's board paper, you will see this one. Gauss's theorem, state and prove Gauss's theorem. Also apply Gauss's theorem to find the electric field due to sometimes sheet, sometimes thin wire, sometimes shell. This is the explanation of sheet. So always we want to write something, right, about what we are going to do. So consider a thin infinite plane sheet of charge with the surface charge density sigma. Okay, surface charge density sigma. So we have to find the electric field, okay, produced due to a thin sheet. That is the topic here. So we have to find the electric field at point P at a perpendicular distance from the sheet. So let me complete this writing, then we can go to the explanation part of it. Okay, just have a look into the text. It is not mandatory to write as it is, but it is required to write something about what we are going to do. Instead of starting rough data, explain the things. Okay, so we are going to find the electric field produced due to a thin sheet at a point P at a perpendicular distance r from the sheet. Okay, r from the sheet. So draw one sheet first. Okay, draw it. Okay, completing here. This is the sheet I am imagine for derivation. Assume this is a thin sheet and the charge density of the sheet is sigma. Now let me mark the point P, which is at a distance small letter r from the sheet. Here is the point P exists. Okay, here is the point P exists. And mark the cross-sectional area of the imaginary cylinder considered here. Okay, one imaginary Gaussian surface. In the other video I explained there is a way of considering imaginary surface. The name of that way of considering is Gaussian surface. Gaussian surface. So here the Gaussian surface is in the form of a cylinder. Now you can see the diagram, a small cylinder, and the cross-sectional area of the cylinder is A. Okay, that point is actually the point P, and the direction of electric field at that area is capital letter E, that is away from the sheet. Why away from the sheet? Because the charge we considered is positive charge. So electric field from the positive charge will be away from the charge. That's why the direction of the electric field is marking away from the sheet on both sides. You can see E. And small letter r also marked here, that is the distance of the point P, that is the two end point of the cylinder from the sheet. Sigma I labeled here, that is the surface charge density. So I think all the area marking, all the labeling finished about the diagram. One more thing to mark actually, direction of electric field on side of the cylinder, that is CS, a curved surface area of the cylinder. That we can mark after few steps. Okay. So what we want to imagine now? Now we want to imagine that Gaussian surface concept, that is, let me write. Now imagine a cylindrical Gaussian surface of cross-sectional area capital letter A, as shown in the figure. You can see the diagram and understand. One imaginary cylindrical surface considered, and the cross-sectional area of that cylinder is capital letter A. Yeah, and that is around the point P. Point P is actually the place where the end of the cylinder. Okay. Okay. And the length of the cylinder is from left to right, r plus r. It is 2r passing through the sheet. Prepare a similar sentence or the same sentence, there is no problem, but it should make sense. Whenever you write something, it should connect with the diagram what you are doing. What is next is the time to write the flux. We already studied how to write the flux. What is the equation for flux? What is the equation? What? Phi is equal to E dot delta S. We will see can we use the here or not. So this is the time to write the flux now. So total flux over the entire surface area of the cylinder is phi is equal to integral E dot ds. Okay, phi is equal to integral E dot ds. So is equal to, remember to mark the vector symbol above E and ds. We are dealing with the vectors. And now when you consider the total flux, actually you can look into the diagram and understand there are three places where flux have to calculate. One is the left side, through that cross-sectional area flux going out. Other one is the side of the cylinder. Third one is the right side of the cross-sectional area of the cylinder. That's why I wrote here flux is equal to integral E dot ds left plus integral E dot ds side plus integral E dot ds right side. Okay. Now angle decide flux exists or not. Look into left side. What is angle between area vector and E? That is 0. Why 0? Because area vector is normal to the surface of left side. Electric field already on the same side. They are parallel, 0. Okay. And when you look into the side of the cylinder, see the mic before in the previous video I told the area vector of this mic is normal side, okay, normal to this one. That is electric field coming towards right in the diagram. Area vector is normal to that side surface. So angle between them 90 does not exist because cos 90 will come. Right side angle between them is same as left side exists. Yeah. So flux is equal to, about left side first expression, okay, integral E ds cos 0, angle between E and ds is 0, plus middle portion E ds cos 90 integral, okay, cos 90. I explained already why it is 90. Then right side again ds and E are in the same direction. So cos 0. So cos 0 value is 1 exists. Cos 90 value is 0 does not exist. Again third one cos 0 value is 1 exists. So what is not exist no need to write, right? So first part exists. E outside because this is actually the constant. E integral ds plus 0 plus E integral ds. Simple, yeah, understandable. That's why I'm not repeating again. So here integral ds in the previous case we wrote integral ds of the sphere is 4 pi r square. But here we are writing the total area is A, just A. A can be anything, right? Depends on the shape. For the sheet it is area, length and breadth will come. So A. So EA plus EI is equal to 2EA. That is the flux produced by a thin sheet. What is? Electric flux due to a thin sheet is 2EA. But that is not the end of the derivation. Okay. So in the next two derivation, application, derivation, till here the method same. After this also method same. Then what is different is area calculation is different. In the case of sheet, area calculation is integral ds is equal to A. The remaining part, what I am writing now, the charge density and all, depends upon the diagram it will come, but method same. So we know that surface charge density of the sheet is sigma is equal to Q by A. Okay. Surface charge density symbol is sigma is equal to Q by A. And charge from this expression you can write after cross multiplying, Q is equal to sigma into A. Look into diagram, possible, right? Why I am writing this one? Because we are going to use this Q value in Gauss's theorem. Remember, this topic is application of Gauss's theorem. So we can use Gauss's law, Gauss's theorem equation now. So the charge enclosed, we found it Q is equal to sigma A from the surface charge density. Yeah, from the surface charge density. Now we are going to write Gauss's law. Okay. Method you see it, the same method followed for next two, only the variable change. So using Gauss's theorem, what is the purpose of Gauss's theorem? Gauss's theorem is used to find the flux. So using Gauss's theorem, flux is equal to 1 by epsilon 0 times Q. This is Gauss's theorem, right? 1 by epsilon 0 times Q. Net charge enclosed is equal to 1 by epsilon 0 times. So total electric flux is equal to net charge enclosed times 1 by epsilon 0 or 1 by epsilon 0 times Q. So substituting now in the flux equation. So phi is equal to 1 by epsilon 0, 1 by epsilon 0, and in the place of Q we will write sigma. So we can write, this is generally sigma A by epsilon 0. So flux is equal to sigma A by epsilon 0. Now look above, there is a equation number 1, phi is equal to 2E. Here one equation you see, phi is equal to sigma A by epsilon 0. Can we do a comparison now? Equation number 1 and 2, possible, right? Because LHS are same. So RHS comparison going to do. From there we will find what is E is equal to. Okay. So from equation number 1 and 2. Method you understood, yeah? We are going to compare the RHS because the LHS of these two equations are same. Okay. Okay, equation number 1 and 4. Maybe you ask where is 3. By mistake I wrote after 2 equation number 4. Okay, from equation number 1 and 4, see RHS of first equation is 2E. RHS of second equation is sigma A by epsilon 0. What is our target now? Get the value of E. Before that one there is a simplification possible, A and A cancelled, so cancelled. So E is equal to sigma by 2 epsilon 0. Okay. Actually there was an extension for this one for thick sheet. For thick sheet the derivation will become E is equal to sigma by epsilon 0. 2 will not be there. Okay, 2 will not be there. Okay, that is not included in this topic. Okay, but refer to that one. Field due to thick sheet also you refer. Okay, where is the change happening is charge density place change coming. In the place of sigma is equal to Q by A, that will become sigma is equal to Q by 2A. That 2A if you maintain in this equation, from the middle you continue, you will get that sigma by epsilon 0. Look into diagram and decide. Here E is independent of R, right? You can see that one. E is independent of R. How is the derivation now? Simple way explained. You like it? If you like it, kindly share with your friends. There are too many friends in your classroom, right? Please share. Let them learn. Okay, students, thank you. Have a nice day. Next video will be about other application. This is the other application. Okay. Thank you. Have a nice day. Bye bye.